survey-grade instrument. It contains the same dual-axis compensator that is used in high-end total stations. The difference is that instead of measuring discrete points, the laser scanner can capture up to 50,000 measurements per second. This results in a very dense cloud of data points, each of which are to the same accuracies as those measured by the total station. With 3D laser scanning, we can collect a large amount of positional data in a very short space of time. A rich data set allows us to visualize and analyze tanks in great detail for efficient inspection and maintenance. The data shown on screen was collected in a little under 2 hours from 10 positions around the storage tank. In total, almost 35 million points were surveyed and coloured by the scanner's onboard camera. The 3D modelling of the storage tank and its surroundings allow us to create a comprehensive data set that can be used to obtain direct measurements and volumes, ensuring that containment dikes, for example, satisfy regulatory requirements. Areas of potential concern or failure can be quickly identified and quantified to reduce repair time. Laser scanning can be used for accurate deformation monitoring. In order to determine the deformation of the tank shell, each individual point is assigned a value using its distance from the centre of the tank, its point radius. Data can be unfurled and laid flat. A plot of deviations allows us to easily visualise outer roundness. Areas coloured yellow show outward deviations, and areas coloured blue show inward deviations. In this image, the deformation colour range has been altered, such that the unfurled surface is coloured green where the tank shell is not furled outward or inward by more than plus or minus 5 cm. This makes the larger deformations more visible, and we can clearly see that when the tank is full, the amount of inward deformation, coloured blue, is reduced, and the amount of outward deformation, coloured yellow, is increased. Radial displacement plots, slices through the storage tank, can be created at any location. The plots here show a measurement for every degree around the tank wall at the 3 different states of fill. We can exaggerate the small differences to better help visualise the deviations. In this case, the largest deviations are approximately 7 cm from the ideal tank shell. These graphs show the variation in verticality throughout the tank wall's height. Create a section from 0 to 180 degrees and also at 90 to 270 degrees. This allows us to report the vertical angle north-south and east-west. Laser scanning allows us to use the millions of points surveyed on the tank wall, which we can best fit a cylinder through. The axis of the cylinder indicates the overall tank verticality. From the scan data, we can analyse the tilt of the storage tank at different states of fill and monitor both the tank and its foundations to quantify changes that may be caused by settlement or subsidence. Whilst the probability of a catastrophic failure of the storage tank is low, such incidents do occur. Failure can be the result of a damaged pipe or valve connection, or even partial removal of a small section of tank wall. Failures such as the one depicted here tend to be sudden events. The 3D model can provide information about the complex